Hi and a very good day. Today we will talk about analysis of acrylamide in fruit products using high performance liquid chromatography or known as HPLC for our case study. It will be presented by Muhammad Ridwan bin Tabrani, Siti Aisyah binti Muzaffar, Nurin Hajra binti Haminullah and Nur Faika Humaira binti Muhammad Sukri. This is the presentation outline. We will start with introduction, methodology, data analysis, conclusion and references. I will start with the introduction of the journal article that we found, which is about the determination of acrylamide concentration in processed food products using normal phase HPLC. Acrylamide concentrations in processed food products have now become a major health concern, which was revealed by the World Health Organization, or known as WHO, and the European Union Scientific Committee for Food (STF). It has been shown in laboratory studies to cause cancers in animals. The purpose of this research is to determine the content of acrylamide in processed food products available on the open market. 3 bakery items, which are vegetable puff, chicken puff, and egg puffs, and 3 fried chips, which from Kurkure, Lay's, and banana chips from 3 different brands were tested for these acrylamide levels. The analysis was carried out using the high-performance liquid chromatography HPLC technology, which provides accurate qualitative and quantitative analysis. The overall concentration of acrylamide was found to be the highest in Kurkure, followed by Lay's, and the lowest is banana chips. Here is the schematic diagram for HPLC. It begins with a solvent reservoir as the mobile phase by injecting the solute at the column. The analytes and the mobile phase are pumped through the column and separation occurs at the analytical column. Peak recorded is the column of the component that elutes first and the readout will be displayed.
And I will continue for the methodology of this case study. For the material, the 3 different fried chips from 3 different companies, which is Kurkure, Lay's, and banana chips. 3 bakery item: vegetable puff, chicken puff, egg puff. Sample preparation: each 25 microgram samples was soaked in 75 ml of water. A solution of 100 gram per kilogram D3 acrylamide in acetonitrile was added. The homogenate was incubated for 30 minutes at 70 degrees C in a beaker glass covered with aluminium foil to keep water from evaporating. When the solid form alarms 10 ml for 8.4 grams of surfactant was transferred to a 25 ml pointed flask, 10 grams of the homogenate was weighed into a 100 ml centrifuge glass with a screw cap and well mixed with the 40 ml of 1-propanol. Around 200 mg of vegetable oil was added and the water of propanol was evaporated in the rotary evaporator set to 50 torr and 60 to 70 degrees C in the water bath. When the no liquids remain, evaporation was stopped. The evaporation residue, which consists of fat or added oil, and typically a lot of salt, was extracted with acetonitrile and defatted using hexane. An ultrasonic bath was used to mix 3 ml of acetonitrile and 20 ml of the hexane with the sample. Using a pressure pipette, the acetonitrile phase was transferred into a 10 ml reagent glass with screw cover. Using acetonitrile rather than taking long hexane, Another 5 ml hexane was used to extract the acetonitrile phase, and 1.5 ml of the acetonitrile phase was placed into a 1.5 autosampler vial. Next, IMS internal study looking at the solution was added. This means 5 microliter of the 25 mg solution in acetonitrile for the 25 gram samples for the 75 ml water. HPLC data analysis. HPLC instrument used was Federax 5 microliter C18 column 4.6 times to 15 mm with mobile phase ACN H2O70, that is acrylamide water. The flow rate was fixed to 0.5 ml over minute and the detection wavelength was set as 202 nanometer. Mode of HPLC instrument was isocratic and injection volume was 20 microliter.
There were 6 that was analyzed: banana chips, chicken puff, egg puff, Lay's, fried chips, and also vegetable puff. For banana chips, it had 13 peaks corresponding with the 6.180 characteristic peak with the highest percentage. Among the 6 samples selected for the study, banana chips had the lowest concentration of acrylamide. Next, for vegetable puff had 16 diffraction peaks with an area percentage of 6.933. The concentration of acrylamide was lower than Kurkure and Lay's. The acrylamide concentration was higher than that found in chicken puff, egg puff, and banana chips. Next, for chicken puff, the acrylamide concentration in chicken puff was moderate, according to HPLC analysis, with 15 distinct peaks and 7.913 having the highest area percentage. For egg puff, an analysis of egg puff analyzed showed 11 distinct peaks, with 7.947 representing the highest area percentage. When compared to chicken puff, the acrylamide concentration in the egg puff sample was found to be quite strong, but it was lower in the vegetable puff. For Lays, HPLC analysis of fried chip Lays, which had the second largest concentration of acrylamide. Lays had 11 distinct peaks, with 7.873 having the greatest area percentage. Lastly, for fried chips, had the largest concentration of acrylamide. There were 22 characteristic peaks discovered, with the 6.767 having the highest peak percentage. Fried chips has the highest acrylamide concentration because of various factors including degree of frying and compositional differences with other processed food items. HPLC has attributed with qualitative and quantitative analysis of biological and non-biological components. By using HPLC to analyze biological component, various flow rates are necessarily based on the underlying composition. The flow rate has a major impact on the time it takes to complete an HPLC analysis. The higher the flow rate, the higher the analysis process.
Assalamualaikum warahmatullahi wabarakatuh. I am Siti Aisyah binti Muzaffar and I will continue with the conclusion. So the processed food sold in supermarkets appear to contain a significant quantity of acrylamide. The chemical reaction that occurs during high temperature cooking appears to result in the production of acrylamide in processed foods. There is no doubting that each of the 6 samples included in the study contain acrylamide, despite there being variances in the amounts present. The absence of acrylamide in processed food products will be very advantageous for the general public's health.
For the next topic, analysis of ascorbic acid in drinks using spectrometry, 20 spectrophotometers, and I will continue with introduction. Fruit juice are popular all over the world because of their health advantages, pleasant taste, and a distinct aroma and flavor. Natural fruit juices are high in vitamins, minerals, soluble and insoluble fiber, and important bioactive substances that are essential for human health. For all of the reasons stated above, vitamin C content in fruit juice is an indicator of quality that must be carefully evaluated in terms of fluctuation during manufacture and storage condition because of the importance and ease of degradation of vitamin C. It is critical to accurately evaluate the quantities of vitamin C in fruit juices. Many analytical methods, including titrometry, spectrophotometry, biological methods, electrochemical methods, and chromatography, can be used to determine the vitamin C content of fruit juices. Because vitamin C may absorb UV radiation, spectrophotometry is one of the most commonly utilized basic procedure. Direct ultraviolet UV spectrophotometry can provide a quick, easy, and reliable approach for determining L-ascorbic acid absorption of UV light by the sample matrix is a key issue due to the interference caused by absorption of the other rays. So, the purpose of this study is to assess the ascorbic acid content of several commercial fruit juices using both titrometric and spectrophotometric methods. The obtained finding will compare to see if there was a significant difference between the two approaches and to choose the easiest, most accurate, and dependable analytical method for the vitamin C concentration in commercial fruit juices.
Assalamualaikum warahmatullahi wabarakatuh. So my name is Nurul Hajira binti Hamdal and I will continue the presentation. I will continue the methodology. The material used is 3 to 5 different types of 5 selected brands of fruit juices. First, the evaluation of total ascorbic acid content in fruit drinks. Number 1. A standard solution of potassium iodide KiO3 was used as an oxidizing agent for volumetric determination of vitamin C. 2. 10 ml samples of each selected fruit juice sample was pipetted into a conical flask where 5 ml of 0.2 m potassium iodide, 2.5 ml of 1 m hydrochloric acid and few drops of starch solution were added. The solution was titrated against the standard solution of 0.01 m KiO3 until dark blue color appeared. The amount of vitamin C in fruit juices was calculated by using following relationship, which are M1V1 over N1 equal to M2V2 over N2, where M is molar concentration, V is volume, and N is moles number. Second, standard solution and calibration curve of ascorbic acid preparation. 1. 0.01 gram of ascorbic acid was dissolved in small amount of 0.5% oxalic acid solution and completed with distilled water. 2. 0.01 gram of KMnO4 was dissolved in 5 m of sulfuric acid in a 100 ml volumetric flask and distilled water was completed to the mark. 3. 1 ml of chromogenic agent was added in a series of 10 ml standard solution with different concentrations of ascorbic acids.
Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Aisyah binti Muzaffar and I will continue with the analysis. So for this case study, the analysis is vitamin C levels in commercial fruit juices were measured 3 times and presented as mean, max, mean, standard deviation, confidence interval, and coefficient of variation. The SPSS version 2022 software was used for statistical analysis and graphs were created with the GraphPad Prism version 8.02 software. The paired sample t-test for equal means for vitamin C content was used to compare the two methods for determining ascorbic acid content in fruit juice samples. Statistical significance was defined as a p-value of 0.05. These are two calibration curves for determination of vitamin C content with different concentrations. So for figure 1, it is the calibration curve for determination of vitamin C content with concentration of AA range 0.124 mg per liter. Then figure 2 is the calibration curve for determination of vitamin C content with concentration of AA range 10 to 100 mg per liter. Commercial fruit juices, apple, orange, cherry, and blueberry from 5 of the most popular and frequently consumed brands were chosen. In our study, we discovered 18 different commercial fruit juices. All samples collected were labeled with a code ranging from L1 to L18. So these are the pH values of fruit juices sample. The table 1 shows that statistical results of pH values of fruit juice samples with range 2.68 to 3.66. Figure 4 illustrates the result of ascorbic acid content in fruit juice samples obtained using two different methods. Both analytical methods were used to evaluate a standard solution of 10 mg per 100 ml of AA. According to the findings, the spectrophotometric method determined a higher level of vitamin C content than the volumetric method. The amounts of vitamin C in samples L1 to L4 of the same brand were highly similar. The largest differences in vitamin C content were found in samples L9 to L16, which are blueberry fruit juices. As a chromogenic reagent, potassium permanganate reacts with other reducing substances in the juice, not just vitamin C. According to the results and other studies, the spectrophotometric method has a higher level of vitamin C content than the dietmetric method. Table 2 presents the statistical results of data obtained using both analytical methods for determining vitamin C content. Vitamin C content of fruit juice samples range from 5.28 mg per 100 ml to 39.93 mg per 100 ml for volumetric methods and from 15.67 mg per 100 ml to 49.33 mg per 100 ml for spectrophotometric methods with confidence intervals ranging from 2.53 to 2.35. The paired samples t-test was used to evaluate the analytical methods used to determine the vitamin C content of fruit juice samples. The results of two cases, L9 and L16, from the set of data underlying the statistical analysis were excluded for the reasons stated above. According to the paired samples t-test, there were no statistically significant differences between the two analytical methods, which shown in the table 3. Based on the test result, statistical tests, and other studies, the spectrophotometric method could be more consistent and reliable if the impact of color interference is considered. The vitamin C content of commercial fruit juice samples were determined a week after they were opened and stored at room temperature, which is 20 till 25 degrees Celsius. The iodometric method was used to determine vitamin C levels. The PET samples t-test indicates a statistically significant difference between means of vitamin C content measured before and a week after, which was decreased as shown in table 5 and which shown in table 4. The PET samples t-test indicates a statistically significant differences between means of vitamin C content measured before and a week after, which was decreased as shown in table 4. Table 5 illustrates the statistical results of the vitamin C content of commercial fruit juice samples before and after opening a package. A week afterward, the vitamin C concentration was found to be in the range of 1.94 mg per 100 ml to 25.16 mg per 100 ml. The total amount of vitamin C losses ranged from 14.2% to 76% when commercial fruit juices were stored in open conditions and at room temperature for 7 days. The calculated average loss was 47.7%. Commercial fruit juices that are consumed quickly after they have been opened have a higher vitamin C content than those that are stored. The storage temperature has a significant impact on the loss of total vitamin C levels. As shown in table 6, the vitamin C concentrations in all analyzed commercial fruit juice samples were higher than those indicated on producer levels. The concentrations of vitamin C in all analyzed commercial fruit juice samples were higher than those indicated on producer levels, as shown in table 6. The p-value is less than 0.05. The declared vitamin C level ranged from 9 mg per 100 ml to 12 mg per 100 ml. Even though time and storage conditions influence ascorbic acid losses, the manufacturer increased the amount.
Next, for conclusion, vitamin C levels in commercial fruit juices range from 5.28 to 39.63 mg per 100 ml when measured volumetrically, and from 15.67 to 49.33 mg per 100 ml when measured spectrophotometrically. The obtained result revealed that the vitamin C concentration of the analyzed commercial fruit juices sample was significantly higher than that indicated on labels by the producer.
Then these are all the references that we refer to for our case study.
I think that's all from us. Thank you.